In this video, we'll have a look at E1 reaction mechanism and regio and stereoselectivity of elimination reactions. Elimination that proceeds through an E1 mechanism is unimolecular elimination. And here is one example. So elimination of hydrogen bromide from tertiary butyl bromide in water as a solvent and a base. Products are 2-bromobutane and aqueous solution of hydrogen chloride, hydrochloric acid. Since this is unimolecular mechanism, reaction rate depends only on the concentration of substrate. So reaction rate depends on the rate constant and concentration of substrate, or as in this specific case, rate constant and concentration of tertiary butyl bromide. Reaction mechanism involves the first slow step, which is a breaking of carbon-bromine bond to give corresponding carbocation, in this case tertiary butyl cation. And then second step is fast product determining step, and in that step base, in this case water, picks up beta proton, and that results in formation of the corresponding alkene. And so now we can summarize reaction mechanism. First step is rate determining step, slow step, formation of carbocation, and second step is product determining step. Now you can understand why this is a product determining step. Because carbocation, as you have seen earlier, can undergo SN1 substitution reaction with a nucleophile. So if reagent is a nucleophile, and same reagent could act either as a nucleophile or a base depending on reaction conditions. So a reaction with a nucleophile will result in substitution reaction, while reaction of carbocation with a base in elimination. So it is the second product determining step where that is determined, whether it's going to be nucleophilic substitution or elimination reaction. So that's why this step is called product determining step. Regiochemistry of an E1 elimination is always Zaitsev. Here is one example. Elimination from 2-chloro 2-methyl butane in water as a solvent gives 2-methyl 2-butene as the major product and 2-methyl 1-butene as the minor product. As usual with Zaitsev eliminations, selectivity is not great. We get 70-30, 80-20, 85-15 maybe ratio of the two regioisomers. Nonetheless, there is always more substitute alkene that is predominant. So in case of E1 elimination, it is always more substitute alkene that is the product. And the reason for this is in the reaction mechanism. When we consider reaction diagram, so first step, rate determining slow rate determining step involves formation of the carbocation. And then in the second step, carbocation loses proton to give corresponding alkene. And this is again second product determining step. In this case, in this product determining step, it is determined what is going to be the pathway of the elimination, so whether more or less substitute alkene will be formed. And a formation of more substituted double bond is favored because the double bond that is being formed, that pi bond that is appearing in the transition state, is more stable and results in lower energy transition state if it has more substituents on it. So those additional substituents stabilize it through hyperconjugation. So again, it is kinetically controlled process, and so it is the second rate determining step where it is determined that the reaction proceeds through Zaitsev elimination to give the more stable alkene, or the more substitute alkene, which is the same thing. E1 reactions, since carbocation is the intermediate, proceed through rearrangements, if possible. So here we have an example of 2-chloro 3,3-dimethyl butane. Upon loss of chlorine, after chlorine leaves as a leaving group, secondary carbocation is formed. Now this carbocation usually does not undergo elimination, or if there is elimination, that will be minor product, maybe about 3%. The major reaction pathway involves, in this case, alkyl shift. So one of the three neighboring methyl groups shifts, moves to the carbon, that is secondary carbocation carbon, and that results in formation of tertiary carbocation. And then tertiary carbocation loses proton to give the most stable alkene as the major product. Of course, as we have seen already numerous times, the most substitute alkene is the most stable one. So in this case, reaction product is 2,3-dimethyl-2-butene. As you can see, carbon skeleton is completely rearranged. Rearrangements also may involve rearrangements to form other more stable carbocations, not just tertiary, but carbocations such as benzylic and allylic. And in this second example, we have an example of rearrangement where after loss of bromine, there is hydride shift to give allylic cation. So secondary carbocation is rearranged into much more stable secondary allylic carbocation, which then undergoes elimination to give, in this case, a diene. Now we are going to examine stereochemistry or stereochemical outcome of E1 and E2 elimination reactions. Stereochemical outcome means whether cis or trans alkene is the major product. First, we are going to look at E2 elimination reactions. So we examined E2 reaction mechanism in the previous video. Now we are going to look at stereochemistry of E2 eliminations. Here is an example of an E2 elimination. So elimination of 2-bromopentene with ethoxide in ethanol gives trans 2-pentene as major product and cis 2-pentene as minor. You can see that these two account only for 55% of the total products, so there are numerous other byproducts that are formed. So how do we explain this stereochemical outcome? Well, we have to consider transition state, obviously, since E2 elimination is a concerted reaction. So let's consider first transition state, labeled here with Roman numeral 1. So in this transition state, carbon-bromine bond on closer carbon, this is obviously Newman projection, carbon-bromine bond or closer carbon is aligned with carbon-hydrogen bond on the back carbon. You can see these two bonds are what we call anti-periplanar. So with anti-periplanar bonds, elimination is possible because loss of these two substituents will result in formation of a new pi bond. We can see that in this transition state, ethyl group on far carbon and methyl group on closer carbon are on the same side. That means they will end up on the same side in the resulting alkene. So this transition state results in formation of cis stereoisomer. And you can also see that there is steric hindrance in this transition state because two substituents are gauche to each other. So that's going to be somewhat high energy transition state, certainly not favored. Then in the second transition state, we rotated back carbon by 60 degrees. We can see that again we have carbon-bromine and carbon-hydrogen bond that are anti-periplanar. Anti means on the opposite sides and periplanar, that means in the same or nearly the same plane. Again, they are properly oriented for elimination. When two bonds are broken, new pi bond can form. But now we can see that ethyl and methyl groups are on the opposite sides, so they are anti to each other. There is no steric hindrance between them, which means that when elimination occurs, the two groups will end up on the opposite sides of the double bond. So that's trans product. Since there is no steric hindrance in this transition state, this is low energy favored transition state. So this explains why trans product is favored over cis. So why trans product is major while cis is minor. We can identify two possible conformations. Another 60 degrees rotation will result in carbon-carbon bond being aligned with carbon-bromine bond. Elimination from this conformation or this transition state is not possible because carbon-carbon bond would have to be broken simultaneously with carbon-bromine for elimination to occur. Those are bonds that are anti-periplanar. And this cannot happen, so this is not a reasonable conformation for an elimination. Finally, in this fourth possible transition state, we have actually an eclipsing conformation. Now we have what we call syn periplanar. So on back carbon, carbon-hydrogen bond is properly aligned with carbon-bromine on the front carbon. They are properly aligned for elimination, but they are syn to each other on the same side, and they are periplanar. But because they are eclipsing, that's very high energy transition state due to high torsional strain and also high steric strain. So this is not reasonable conformation or reasonable transition state except in some cyclic compounds. So this is very rare transition state, occurs only in some cyclic systems, and generally you should not consider it because that would be a more advanced topic and you will not encounter that in an introductory organic chemistry course. Now let's examine stereochemistry of E1 elimination reactions. Here is an example, elimination from 2-bromobutane. It can give trans-2-butene and cis-2-butene, and trans-2-butene is the major product. Now, since the intermediate is carbocation, we should consider stability of the possible carbocations that lead to elimination products. So first one is carbocation where front carbon is carbocationic carbon. So this is obviously Newman projection. So front carbon is trigonal planar, and there is vertically shown atomic empty p orbital of carbocation. On the back carbon, one of the carbon-hydrogen bonds has to be aligned in the same plane, so it has to be planar or periplanar, which means nearly the same plane. So it has to be in the same plane as the atomic empty p orbital, so that when proton is removed, molecular pi orbital can be formed. We can see that in this carbocation, two methyl groups are on the same side. There is considerable steric hindrance between them, and that's not very stable carbocation. Not impossible, but not very stable. Since they are on the same side in carbocation, upon loss of proton and formation of the pi bond, those two methyl groups will end up on the same side of the double bond, which means that now we have cis isomer. So a carbocation that leads to formation of cis isomer is not particularly stable. Now, if we rotate carbocationic carbon, closer carbon to us, by 180 degrees, we end up with second transition state. And again, we have carbon-hydrogen bond on the back carbon that is aligned with atomic p orbital on the closer carbon, and now two methyl groups are on the opposite sides. It's very close to an anti-conformation. And so upon formation of the molecular pi bond, the two methyl groups will end up on the opposite sides of the pi bond or give trans-alkene. This is low energy carbocation, certainly much lower energy carbocation compared to previous one, and that's going to be the favored one. So that's why formation of trans double bond is favored over cis. Third possibility involves a third bond on the back carbon that is aligned with empty p orbital, but that's carbon-carbon bond. Since carbon-carbon bond cannot be broken in an elimination reaction, this carbocation does not lead to formation of a product. So this conformation is not relevant. We don't consider this conformation, simply it cannot result in formation of elimination product. It's only 1 and 2 carbocations that can result in elimination. So stereochemical outcomes of both E1 and E2 elimination reactions are the same. In both cases, more stable trans-alkene is formed, but for different reasons. In case of an E2 elimination, it was the stability of the transition state, while in case of E1 elimination, stability of the intermediate carbocation. And so here is a summary. So first reaction would be E2 elimination, and you can see major product is trans-alkene. And second example, E1 elimination, again, major product trans-alkene. Now we are going to look at regiochemistry of elimination in cyclic compounds. E2 elimination is actually somewhat complex. And here is an example. Elimination from 1-bromo-2-methyl, or trans, that's important, trans 1-bromo-2-methyl cyclohexane, with tertiary butoxide as a base, proceeds to give 100% 3-methyl cyclohexene and 0% 1-methyl cyclohexene. That's actually a somewhat surprising result. At first glance, it may appear to be Hofmann elimination, but actually both Hofmann and Zaitsev eliminations give mixtures of products. They may give 70-30, 80-20 mixture products, maybe 85-15 if selectivity is good. But 100 to 0, that's actually something else. So that tells us that something else, some other processing is involved, and it's not simple Hofmann or Zaitsev elimination. So to understand what is happening in this case, we need to look at mechanism in detail. We need to look at conformation of compound that is undergoing an elimination. And so when we consider the most stable chair conformation, so di-equatorial conformation, where both bromine and methyl are equatorial, we can see that carbon-bromine bond, which is shown in bold, has two bonds that are antiperiplanar to it. From analysis we just completed, you have seen that in transition state, bond that is being broken together with carbon leaving group bond has to be antiperiplanar to it, so that new carbon-carbon pi bond can be formed. So bonds that are antiperiplanar to carbon-bromine bond are shown in bold. And you can see that both of them are carbon-carbon bonds. And carbon-carbon bond cannot be broken in the course of an elimination reaction. That means that an elimination reaction is not possible from the more stable di-equatorial conformer, because only carbon-carbon bonds are antiperiplanar to the carbon-bromine bond. So we need to flip this conformation into less stable diaxial isomer. And you can see that elimination is possible only from the less stable diaxial conformer, because it has one carbon-hydrogen bond that is antiperiplanar to the carbon-bromine bond. And you can see that that bond is bonds on the carbon that is away from the methyl group. So carbon of the cyclohexane ring that is away from the methyl group. And then elimination, of course, results in formation of 3-methyl cyclohexene. So that's the result, that's the reason for the observed regiochemistry. And from this we can draw a conclusion that in the course of an E2 elimination from 5 or 6 membered ring, the two groups that are eliminating must be trans to each other. So only groups that are trans to each other, in this case hydrogen and bromine atoms, they have to be trans for E2 elimination to occur. Cis groups cannot eliminate. And we can prove that by carrying out a study on this particular compound that has bromine on 6-membered ring, and on one side there are 2 methyl groups. So elimination towards those methyl groups is not possible. The only possibility is that one of the 2 hydrogens is eliminated on the other beta carbon. So one beta carbon has 2 methyl groups, the other one has 2 hydrogens. But we have labeled isotopically those 2 hydrogens. One is ordinary hydrogen, protium, the other one is deuterium. And protium is cis to bromine, deuterium is trans. Upon elimination, all of the deuterium is removed from the product. All of the deuterium is lost and all of the protium is retained. So that shows the 2 groups that are eliminating in an E2 elimination from small rings or rings like these, 5 and 6 membered rings, must be trans to each other. E1 elimination from cyclic compounds proceeds through carbocation as reaction intermediate. And the final outcome is that the most stable, the most substitute alkene is formed. So here we have an example of elimination from 1-bromo, 1-methyl cyclohexane, and product is 1-methyl cyclohexene, 99%. Methylene cyclohexene is formed in only 1% yield. The reason for the observed regioselectivity is that intermediate carbocation can eliminate by elimination with any of the carbon-hydrogen bonds or any hydrogens from the neighboring beta carbons that can align properly with the empty atomic p orbital. And there are a lot of, as you can see, a lot of such hydrogens. And of course, when that's the case, then the most stable alkene is going to form. In this case, such hydrogens are shown in bold, and you can see there are 3 beta carbons, 2 on the ring, 1 outside the ring, 1 methyl group, and any of those beta carbons has a hydrogen that is suitably positioned for elimination. Here is one other example, elimination from 1-bromo, 1,2-dimethyl cyclohexane, and it doesn't matter whether it's cis or trans. That's why this 2-methyl group is shown with wavy line. It could be cis or trans, or it could be a mixture. Intermediate carbocation is formed upon loss of bromine, and then upon elimination, the major product is tetra-substituted double bond, so 1,2-dimethyl cyclohexane. So the most stable, the most substituted double bond. Minor product is tri-substituted double bond. That's 1,6-dimethyl cyclohexane. Exocyclic double bond where one carbon is attached to the ring and the other one is outside the ring, is actually usually rather unstable double bond. And so for that reason, such compounds don't form easily. They are actually rather difficult to form. In the next semester, you will learn some reactions like Wittig reaction where we can form such compounds, but they require special procedures. So such compounds will form only in trace amount. And in addition, here such double bond would be only disubstitute double bond, so we wouldn't expect its formation anyway. So in conclusion, E1 elimination proceeds through carbocation, and a product is always the most stable, the most substituted endocyclic, which means inside the ring, double bond. Next, we are going to look at a competition between E1, E2 and substitution elimination reactions.